Welcome back, everyone. It's good to see you all here for some AP statistics. And today we're going to start in on our confidence interval for the mean of a population. So without a whole lot of to do, I'm sure you know what we're doing now. We're going to go ahead and jump right into it. This is another one of those fun days in class. On a good day, I would actually have some Oreos out for you guys to sample while we do this. But you're not actually going to be weighing cookies, although maybe we should try that one year. Most of this can be done without that kind of direct measurement because all of the measurements are here. So maybe I should just read. Here. So Mr. Ferreira wants to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. Okay. He selected a random sample of 30 cookies and found the weight for each cookie. The mean weight for the sample of 30 was X bar equals 11.1921 grams, with a standard deviation of SX equals 0.0817 grams. Make a 95% confidence interval to estimate the true weight of an Oreo cookie. First question we might want to ask is, what is the point estimate of the true mean? Point estimates are always statistics, and the statistic here is 11.1921 grams. So that is the point estimate. More things to think about. What is the population, the parameter, the sample, and the statistic? Always a good thing to have whatever those four things are in mind. Population, of course, is just all Oreo cookies. This makes a parameter mu, which would be the true mean weight of an Oreo cookie. The sample is that subset of all Oreo cookies, which in this case would be just my sample of 30 cookies, 30 Oreo cookies. And this completes with a statistic, which would be X bar, and that is the sample, or the average of my sample, which was 11.1921 grams. Was that sample a random sample, and why is that important? Well, the answer to the first part here is yes, it's a random sample because, quote, he selected a random sample. So sometimes, or oftentimes, I like to quote part of the question to qualify some of these conditions. And don't forget that a random sample allows us to generalize the results to the population. That's why it's important. And like before, I think 2 days ago or 2 lessons ago, this is our condition 1, either a random sample or a random assignment. What is the formula for calculating the standard deviation for the sampling distribution of X bar? This should be a review. What is the formula for calculating the standard deviation of the sampling distribution of X bar? That is sigma X bar equals sigma over the square root of n. What condition needs to be met to use this formula? Just like last time, we need to meet the 10% condition. The 10% condition is met because 30 cookies is less than 10% of all Oreo cookies. And remember, the way I like to quickly calculate that is 30 times 10 is 300. So if there are more than 300 Oreo cookies, then the 10% condition is satisfied. And this is condition number 2 of our confidence intervals for our mean. It's the same condition from our previous confidence interval for a proportion. And remember, this needs to be met because we're sampling without replacement. So we need to be sure that sampling without replacement is close enough to sampling with replacement, or independence samplings. Strictly speaking, when we sample without replacement, then it is not, we're not creating independent probabilities. But if we have a small enough sample in comparison to the population, then the difference is negligible. That's why we need to meet this condition number 2, the 10% condition. In the formula for standard deviation of the sampling distribution of x bar, we don't know the value of sigma. Remember that the value of mu comes from the value of, or the value of sigma comes from the value of mu. Or you need to know mu to calculate sigma. And if you knew mu, then why are you bothering estimating what mu is? So under almost all circumstances, we actually don't know the value of sigma. So just like before, we are going to use the standard deviation of the sample to estimate the standard deviation of the population. We did that before with proportions when we used p hat to estimate p. So the standard error, SE of x bar, this time we're doing x bar, is equal to sigma over square root of n and is approximately equal to Sx over root n. Remember, the difference is sigma is the standard deviation of the population, while S is the standard deviation of the sample. Substitute the numbers in there. That's 0.0817 divided by the square root of 30, and that's 0.0149. Sometimes a question gets asked, how many decimals do I need for this standard error? And the answer is just go to as many decimals places as you put your mean. So if I scroll up here, we can see that the mean has 4 decimal places. So my standard error here is also going to have 4 decimal places. It's a good way to do this. Would it be appropriate to use a normal distribution to model the sampling distribution of x bar? Justify your answer. Now this is kind of a callback to when we were studying sampling distributions. We saw that there are 2 different ways that we can use a normal distribution. And the first one is, if the population is normal, then we can use a normal distribution. Now, when I go up to the question, there is nothing here that says that the population is normal. So we can't use that first one. So we better hope that the sample size is large, which is another way of saying, is the sample size greater than equal to 30? And the sample size, as luck would have it, is exactly equal to 30. Since n is equal to 30, and that's greater than equal to 30, we can use a normal distribution because of the central limit theorem. The central limit theorem. There's a common misconception here that anytime you have a sample size greater than 30, you're just going to say central limit theorem. And that is wrong, because the central limit is only for a mean. Do not use the central limit theorem if the question is about p. You will get burned if you try to use central limit theorem for a confidence interval involving p. And this is all condition number 3, normal. As we see, there are 2 ways right now of satisfying condition number 3. Either we start off with a normal population, or we have a large sample size. So when finding the margin of error for a confidence interval for a proportion, we used z star. For a mean, we're going to have to use something different. We're going to use something like t star. Now, a t star, the t curve is basically the normal curve. So it is the normal curve. But the thing that makes it different is that the probabilities on the t curve are a little bit bigger than they would be on the normal curve. So the reason that we want to use a t curve, so we need to use that t curve because the increased area in the curve is needed to account for the error recreated when we estimated sigma with Sx. Estimating p with p hat, that is not That doesn't create as much error as estimating sigma with Sx. So because of that extra error, we're going to have to use increase area. Basically, we're going to make the confidence interval bigger than it would be had we used the normal curve. So the normal curve has a smaller confidence interval. The t-curve makes that confidence interval just a little bit bigger because of that estimation we did. So here's kind of a exaggerated difference between the t-distribution and the normal distribution, which is sometimes called the z-distribution. And let's think about what would happen if we were doing a 90% confidence interval. Well, with the z-distribution, we know that the area over here in the tail would have to be 0. And I got that wrong. Hold on. There we go. The area would have to be 0.05, and that gives us a z-score, a z-star of 1.96. Now, if we take a look at the t-distribution, the t-distribution is a lot fatter. I hate to say fatter, but we're just going to say fatter. So in order to get that 5% area on the t-distribution, and whoops, you're going to have to forgive me, I made another mistake here, but for a 90% confidence interval, z-star is 1.645, and this tail area is 0.05. So this is where it would be for a standard normal distribution, 1.645. In comparison, the t-distribution is a lot thicker on the edges. So I don't need to go all the way to 1.645 in order to get an area of 5 under the t-distribution, because the distribution is taller. In order to get that same 5% area, I need to make my t-star 1.699, which is a little bit to the left, or should we say a little bit bigger than 1.645. And that little extra biggerness, because of the bigger critical value, that's going to make my confidence interval just enough wide to account for the error created by using S instead of sigma. So T star is always bigger than its corresponding Z star. And yeah, hopefully that works. Hopefully that explanation works. T-curves always work. Okay, let's continue on here, and we have what T star is needed for this confidence interval. Use table B and degree of freedom equals n minus 1 to find it. The t-distribution needs one more piece of information in order to give you the correct critical value. And the piece of information it needs is the sample size, but not actually the sample size, one less than the sample size. They call that number the degrees of freedom, which sounds like the album title to my progressive rock band that I created in the 70s. Let's look at the calculator. Inverse t is going to be the function that we use, just like we used inverse norm for the z-curve and its critical values. We're going to use inverse t to find the critical value on a t-curve. So it's going to be computed exactly the same way. The area is going to be half, so 0.5, multiplied by 1 minus our confidence level, so 1 minus 0.95, because we have a 95% confidence interval. And degrees of freedom is always going to be the sample size, 30, minus 1. Yes, you could put a 29 there. So degree of freedom, inverse t, and we get, look at that, negative 2.045. And that just kind of shows you the t critical, even for the same area, it really depends on the sample size. So a large sample will have a smaller t star. In our case, we got negative 2.045. So on your paper, just like with the inverse normal, since we're doing so much here, we're just going to shorthand how we find our t star. And t star is going to be equal to the inverse t, area equals 1/2 of 1 minus 0.95, comma, degree of freedom equals 30 minus 1. And that gets us 2.045. Just like with the inverse norm or with the confidence critical value for z, the t star is always also going to be a positive number. So even though we got a negative 2.045, our t star is actually positive 2.045. Next thing we have to do is calculate the margin of error, and that's going to be the critical value multiplied by the standard error. In this case, our critical value is t star, and our standard error is s over root n. Okay, let's substitute numbers, and then finally do the multiplication. This gives me the margin of error of 0.305. Calculate the 95% confidence interval using the point estimate plus or minus the margin of error. And that gives me 11.1921 plus or minus 0.305. We're going to interpret that interval using our sentence frame that we always use. So we are 95% confidence that the interval from 11.1616 to 11.2226 grams captures the true mean weight of Oreo cookies. We'll read this one more time for readability. We are 95% confidence that the interval from 11.1616 grams to 11.2226 grams captures the true mean weight of Oreo cookies. And that sounds good to me. As we were doing this process, hopefully you saw that it was really similar to the same process that we used for proportions. In fact, you could pretty much copy and paste the entire thing and make a couple of tweaks here and there, and that would give you the confidence interval for a mean. Write the specific formula for the confidence interval for a population mean. Well, let's start off with the formula for any confidence interval. That's the point estimate plus the margin of error. And let's think to ourselves, what is the point estimate in this case? Yeah, that's bar x. And then we just spent some time finding the margin of error, so we should have that formula. By way of kind of unfolding this, the margin of error is always a critical value multiplied by the standard error. Our critical value we just found was t star, and our standard error is s over root n. So that looks like our specific formula for the confidence interval for a population mean. It looks a lot more compact than the specific formula for a population proportion. And actually, I don't think we need that multiplication sign. And I will just leave it. So, according to Nabisco, an Oreo weighs 11.3 grams. Does the interval provide convincing evidence that the true weight is less than 11.3 grams? Well, let's see. All plausible values for the average weight is 11.16 to 11.22. And that says that every plausible value for the true average weight is less than 11.3. So if every plausible value for the true average weight is less than 11.3, then that sounds like we have convincing evidence that the true average weight is less than 11.3. To kind of come at this from a different angle, 11.3 is not a plausible value for the true average weight of an Oreo cookie, because 11.13 is not between 11.16 and 11.22. And since 11.3 is above the interval, it's greater than the interval, then the true average weight of a Oreo cookie has to be less than 11.3. So that's kind of it for us today. This kind of ran a little bit longer than what we usually do here in AP Stats. Well, maybe not too much longer. We've only been at this for about 20 minutes. But hopefully you get the idea about how these confidence intervals work. Like I said last time, this is pretty much the same routine that we did for the proportions, and there's just a couple of slight tweaks that you need to make, most notably that T star needs to be used. So, that said, I'll see you guys next time, and have a great day.